Okay, yeah, welcome back everybody to part two of this series where I will introduce infinity categories. And yesterday we saw that the theory of infinity categories more or less behaves like the theory of ordinary categories, as long as you replace all the notions of equality by saying homotopy. So most of the theory just works. Today we are gonna see an example of a notion which doesn't really exist in ordinary category theory. It's called the notion of a stable infinity category. And it really uses the fact that we have homotopies in our infinity categories. And another thing we're gonna discuss is symmetric monodal infinity categories. And this requires a bit of, how do we actually deal with algebraic structures in the infinity categorical context? They are a bit more subtle than in the usual setting of ordinary category theory. Okay, but let's start with stable infinity categories. Let me start with a definition. So C denotes some infinity category, and we call it pointed if it has a zero object. So a zero object is an object which is both initial and terminal. So recall that it means for any other object, the home space into zero is contractible and the home space out of zero is contractible. So for example, if C is an ordinary category, we may think of the category of abelian groups. There we have the zero group. It's both initial and terminal. Maybe we think of the category of pointed sets. The point is both initial and terminal in that category. And then we can define what it means for C to be stable. There are three conditions. The first is it is pointed, so it has a zero object. The second condition is it admits all pullbacks and all pushouts. Maybe to emphasize, this is an infinity category, so these pullbacks and pushouts will behave. I mean, this is allowed to be an infinity category, so pullbacks and pushouts behave like homotopy pushouts and homotopy pullbacks. And then the third condition is that a commutative square of the form x, f, y, g, z and w is a pullback square if and only if it is a pushout square. So the definition of this being a pullback square means that this object x is equivalent to the limit of the diagram with y, z, and w. And this square being a pushout square means that z is the co-limit of the diagram involving x, w, and y. So this, if you've never seen this before, it might look a bit mysterious. So first, to make a bit more sense of this, let me write down some examples of pushouts and pullbacks that have special names in an arbitrary pointed category. So definition. If we have some pointed category, we get a notion of fiber or homotopy fiber, if you prefer. Homomorphism from y to z is a certain fullback, namely, it's the pullback where we take W to be the zero object. So we have our map Y to Z. We have the essentially unique morphism from 0 to Z, and then we can take this pullback. And so far, for example, if C happens to be the category of abelian groups, this would just be the kernel of G. But if C is like the category of pointed spaces, then this is like the homotopy fiber. Because this commutative square, there are always homotopies filling these squares. I just want to remind you that commutative squares in homotopy theory always needs these homotopies around. A special case of a fiber is if Y is also the zero object. So the loops of Z is a certain pullback. It's omega Z. So why is this called loops? Well, for example, if you do this construction in pointed spaces, then a map into this pullback will need a map into the terminal object, which is no data. But then you also need the data of an homotopy between the constant map and the constant map. So it consists of a bunch of paths in Z, a bunch of loops. And dually, we can turn things around. We get notions of cofibers and suspensions. The cofiber of F from X to Y is a certain push-out. We have X to Y. We have the unique map to 0. And then we just form the co-limit of this diagram. And then as a special case, we get suspension. Is the case where Y is the zero object. It's called sigma X. Okay. So with this terminology, we can go back to the definition of stable, and I want to write down some equivalent characterizations of what it means for C to be stable. The theorem or proposition, maybe I would call it proposition. If C is a pointed infinity category, the following statements are equivalent. The first condition is that C is a stable infinity category. The second condition is that we might not necessarily have all pullbacks and pushouts, but at least we have fibers and cofibers. And then we ask this third condition only in the case that W is the zero object. So such a commutative square is a fiber sequence of, I'm going to call a commutative square a fiber sequence just if it's a pullback square, because that means that X is the fiber of G. If and only if it is a cofiber sequence. And again, cofiber sequence just means that it's a pushout square, but I'm calling it like that because that means that Z is the pullback, is the cofiber of F. Okay, so it's clear that 1 implies 2 because it's just a special case. The third condition, it looks a little bit different. It's saying, well, we still ask that C has all fibers. In particular, it admits a loop functor. We can take any object Z and we can form its loop space. And this construction is going to be completely functorial because taking limits is functorial and forming the diagram with 0 and Z and 0 is functorial in Z. And we require that this loop functor is an equivalence. And then fourth is a dual condition. T has co-fibers. In particular, it has a suspension functor. And we require the suspension functor to be an equivalence of infinity categories. So yeah, if you're this in the end, this loop space functor is going to be some kind of shift functor, which is going to be invertible. And then this suspension will be shifting in the other direction. Okay, so I want to sketch a little bit of proof of this statement just because it might give you some intuition. But before I do that, I want to make a remark about this second property. And I want to relate it to a property you're familiar with in the context of abelian categories. So in the context of abelian categories, what we are considering is an additive category. And here I really mean an ordinary category that you're used to. Being additive means that all the home sets are actually abelian groups, and a composition defines maps of abelian groups. So what does it mean for A to be abelian? Let me rewrite the condition of A being abelian in a way which very much resembles the second condition over here. So it means that for any commutative square, X with some monomorphism into Y and some epimorphism into Z we have that it's a pullback square even only if it's a push-out square, but we can be more concrete what it means. So we have that X is isomorphic to the kernel of P if and only if Z is isomorphic to the co-kernel of I. So what it basically says is if Z is just the co-kernel of I, then we can recover I by taking the kernel of this map. And conversely, if we have any P and we first form its kernel and then the co-kernel, we recover P. So monomorphisms and epimorphisms are regular. And this condition is very similar, except that we drop the condition that maps involved are monomorphisms or epimorphisms. So this has huge consequences. So it won't be true that stable infinity categories are abelian, and it will not be true that abelian categories are stable. But it's just a helpful analogy to sort of see, a lot of things we can do in abelian categories sort of have analogs in stable categories. So it might sort of make this condition a bit less mysterious. Okay. So yeah, let's see a sketch of proof why this is true. As I already mentioned, it's clear that 1 implies 2, because 2 is really a special case of 1, where we take the object W to be the 0 object. 2 implying 3 and 4 is also not super difficult, so I will just spell it out. First of all, in 2, we assume we have all fibers and co-fibers, so that condition is fine in 3 and 4. So we need to show that omega and sigma are equivalences, and we're going to show that they're inverse to each other, actually. And how are we going to do this? Well, we can consider the square that defined omega of Z. This is a certain type of pullback square, and it's precisely the one of the form that appears in 2. And therefore, by the condition, it's also a push-out square. Which means that the suspension of this object is going to be equivalent to Z. So there is a natural isomorphism between suspension of omega of Z and Z. So this shows that sigma is a left inverse of omega. And conversely, it's going to be a right inverse by just dualizing this argument. Dually, maybe I shouldn't say conversely, but for x, the square defining the suspension is by definition a push-out square, but then by stability, by condition 2, it's also a pullback square, and it gives a natural isomorphism between x and omega of sigma of x. So this shows that sigma is both a left and a right inverse of omega, and therefore they're inverse equivalents to each other. And then the fact that, so 3 is just a dual condition of 4. So if we show that 3 implies 1, then we also get that 4 implies 1, because condition 1 is self-dual. You can just apply the proof to the opposite category, and you will get the other implication. So so this argument I'm not going to write out completely because of time reasons. But let me just give you the main ingredients. If we are given part of such a diagram, we have x, y, and w. We already know, we have assumed that fibers exist. So what we can do is pass through fibers a bunch of times. And then if you have, at some point, you have taken so many fibers that you're going to get loop spaces of x and w and y. So I won't be very precise. I won't tell you about the details, but the point is that you can construct a new square of the form omega x, omega y, and omega w. And you have now extended it by some object a over here. And this is a pullback square. And now we can use the assumption that omega is an equivalence to apply the inverse of omega to this. So we can extend this square to a pullback square like this. And because omega is an equivalence, it turns out that this extension is actually sort of unique. And if you have proved that, then it will follow that any such square happens to be a push-out square, so you know that push-outs exist. Then every push-out square you can deduce that it's a pullback square and so on, and then the claim follows. Okay.
Is there any characterization of stability that only requires the existence of loop and suspension and some properties that they satisfy?
I'm not sure. I'm not sure. I mean, it is very close to this, right? I mean, you're saying don't even assume all fibers, just assume you have omega.
Right, in terms of
I'm,
existence.
yeah, just existence of omega. I wouldn't, I don't, sort of for meta reasons, I don't expect so because I would have expected to see that statement. So, yeah, but I don't, yeah, I don't know.
Thanks.
So let's see. Yeah. So this notion of stability, as I already indicated by making the analogy with abelian groups, it's sort of very important in homotopy theory. We're gonna, see more of it tomorrow. For example, the KK category will be a stable category, and it is very closely related to the notion of a triangulated category that you might have seen before. So I just want to quickly explain how this is related. So first, we should say something about the homotopy category. Every infinity category C has a homotopy category which has the same objects. But now the home sets are going to be given by homotopy classes of morphisms in C. So the morphisms are also just morphisms from X to Y in C, except that we identify two morphisms if they are in the same path component of this topological space. And then if C is a stable infinity category, then the homotopy category will be a triangulated category. So I won't recall what the precise definition of this is, but for example, let me just say some facts that are in particular true. So it has direct sums. Co-products are the same as products. Why is this the case? So if you have X and Y, we can write down a diagram like this, where the map from here to here is in the first variable the identity on X, and in the second one, it's the zero map, the one that factors through 0. And here it's the map 0, comma identity on Y. And this square is always a pullback square in any category, because you can just write it as, in any pointed category, let's say, you can just write it as X times the 0 object and 0 times Y. And here we have 0 times 0. So this is always a pullback square. And then by stability, it's also a push-out square. Which means that the push-out, which is just the co-product of X and Y, is isomorphic to the product. And this is what we mean by having direct sums. So this object is now going to be called X plus Y. Another property is that we have distinguished triangles. The distinguished triangles are going to be sequences of the form f from x to y, g from y to z, minus h from z to, yeah, okay, I didn't say, okay, so this having direct sums already means that the home spaces will, I mean, the home sets are a billion monoids. You can actually prove that they are a billion groups with a similar type of argument. Maybe let me not go into that, but that's what I'm using when I write minus h there. And the distinguished triangles are really the co-fiber sequences in um, C. So we have push-out squares of this form with f and g here. And now if we form another push-out over here, then this is going to be the co-fiber of g. But because push-out squares compose, if we paste this push-out square with this one, the outer squares are going to push out square, and it follows that the object over here is going to be the suspension of x. So this morphism is h, and then this distinguished triangle will have minus h here. And all the axioms in a triangulated category are axioms about these kind of distinguished triangles, and they are basically just formalizing the property that z is the co-fiber of x and y, of the map f. So yeah, you can deduce all of them. Okay. But maybe I should emphasize a bit that the nice thing about stable categories as opposed to triangulated categories is that these co-fiber sequences actually have a universal property. So for example, a tricky thing in triangulated categories is that these like some of these axioms, you have like an existence statement about a certain map, but it might not necessarily be unique and so on. And in the stable category, it is simply unique. You have to remember a bit of the data of the homotopies in the squares. That's the sort of disadvantage. You have to remember a bit more data. But you get a lot of nice things in return. Okay, so now let's discuss the primary example of a stable infinity category. So similar to how the main example of an infinity category is the infinity category of spaces, we'll now introduce the infinity category of spectra. And more generally, we can define what the stabilization of an infinity category with finite products is. Finite limits, I guess. So let's see. Let me first convenience assume it's a pointed infinity category. So we assume it's pointed and it has pullbacks. In particular, we have the omega functor, and it's stable if omega is an equivalence, but it might not yet be an equivalence. So what we can do is just formally turn it into an equivalence by taking a certain limit. So I'm taking a limit of infinity categories. So formally, yeah. It's a certain limit in cut infinity. There are some subtleties with size issues. I have to make sure that C is a small infinity category, that it is even contained inside here. Maybe I don't want to go into details because it's not really the point which is relevant right now. And then in particular, we get an infinity category known as the infinity category of spectra. So what are objects in this? Yeah, by the way, and this denotes the category of pointed. Oh wait, I should let me write spaces here for concreteness. So this is pointed spaces. For example, defined as the localization of the category of topological pointed spaces where you invert all the weak equivalences. What does it mean to be an object in the stabilization of C? Well, an object is just a functor into this out of the point. And this is a limit. Oh, wait, I forgot to write limit here. Sorry. This is a limit. So to define a functor into it, we have to provide a functor into each of these categories and make sure that they are compatible. So we need a collection of objects, X, N, together with isomorphisms in C of the form Xn equivalent to the loop space of Xn plus 1. And I say isos, but if you have like, a category like pointed spaces, then it's really an isomorphism in the infinity categorical sense. So it should be interpreted as a homotopy equivalence, not as an, isomorphism of topological spaces. And what I said that this is somehow the universal way of turning this into a stable category. What do I mean? First of all, it is stable. And in the way I described it, it seems like, this is just a completely formal thing because you have inverted this omega, but it's slightly more subtle because there are some non-trivial endomorphisms of omega squared that are floating around that you have to deal with. But you can prove that this stabilization is actually stable. And furthermore, it has a functor to the original C, which just sends such a collection Xn to the very final object in the sequence, X0. It's sort of the universal way of turning C in a stable into a stable category. So for any other stable category T, stable infinity category, we get an equivalence between functors from D into the stabilization of C Then we can compose by this omega infinity functor to go into functors from D to C. And then here, this superscript, it stands for lex. And what it means is I only restrict to those functors which preserve the terminal object and preserve pullbacks. Or another way of phrasing it is they preserve all finite limits. And the claim is that this is an equivalence. And morally, what the reason is that inside D, you can also form this omega, but in D, it's invertible. So if you have your original functor f and you want to lift it to this limit, what you're just going to do is you're going to, you can first extend it to a functor into here because the omega here is invertible, and then you extend it into here because omega is invertible, etc., etc., and then you can extend it to a functor into the limit. So this is the way to produce, given an f, to produce the extension into the stabilization. Okay, let's see. Yeah. And maybe a nice consequence of this is that any stable infinity category has an enrichment in the infinity category of spectra. So in the same way that, in a billion groups, a billion category, the Hom sets are automatically a billion groups. In the same way, every stable category, the Hom spaces are automatically going to be spectra. For C stable, the functor Hom C from C up times C to spaces uniquely, essentially uniquely, lifts to a functor, which I'm going to call the mapping spectrum, from C up times C into spectra. And by lifts, I just mean if you apply the functor omega from spectra, omega infinity from spectra to spaces, this functor here, you get back your original functor. And we just apply this universal property of stabilization, or if we fix a variable, then mapping out of X is a functor from C into spaces. And this preserves all limits, in particular finite limits. Yeah. Okay, I guess I should have made a remark about why it first lifts to pointed objects. But let me, this is just a proof sketch, I guess.
Is this corollary a special case of if C is not stable, then I can take the stabilization and I in general would get a square instead of a triangle?
Um, so you're asking if it's not stable, do I get spectra in C up times spectra in C goes to spectra, and here C up times C goes to spaces, omega infinity.
Yeah.
I don't think that, does this commute? I don't think this commutes because it would say the underlying space of the mapping spectrum in the stabilization is just the home space between their omegas, which seems false. So I think this doesn't commute. So the answer is, I think, no.
Okay.
But, you know, I'm not, yeah. It's always dangerous to make these statements when you haven't thought enough about it, but
This part you maybe need to let this pass.
wait. Um, so the question is, do I need left exactness? Oh, yeah. So, okay. So the question was, for the statement to be actually true, I need to say that it uniquely lives to a functor which preserves finite limits in both variables. Maybe let me just write it like this. But you can make a uniqueness statement if you're careful about what properties that functor satisfies. Namely, it needs to preserve finite limits in both variables. Okay, let me erase this. Okay. So one example is this category of spectra. Another example is another category we have seen yesterday. We had this infinity category BR, which is obtained from chain complexes by formally inverting all the quasi-isomorphisms. And if you do this in the infinity categorical sense, then this is a stable infinity category. And the underlying triangulated category is the one you're familiar with, probably. I mean, yeah, and in this case, the loop functor is just a functor that shifts the chain complex to the right. The suspension functor is just the functor that shifts the chain complex back to the left. There are many notions in homological algebra, like derived tensor products, for example. Can be just phrased as structures on this stable infinity category. For example, you know, the derived tensor product corresponds to a symmetric monodal structure on dr, and the derived hom corresponds to the internal hom in this infinity category dr. So this is somehow the ext, the Tor functors, and this corresponds to the ext functors. Okay, so now the next thing I want to do in the last 15 minutes is discuss a little bit what these symmetric monodal structures are in the infinity categorical context. And before talking about symmetric monodal infinity categories, let's talk a bit more generally about how to write down what the notion of a commutative monad is in the setting of infinity categories. Okay, so let's think about for a second what a commutative monad usually means. So we have a set M together with an addition map and a zero element, which I will write as a map from the point to M. And then we have a bunch of relations, x plus y equal to y plus x, x plus y plus z is equal to x plus y plus z, etc. I mean, and we have also unitality. You might think, okay, everybody knows this. Why am I writing it down? I'm writing it down because I can now point at these equalities and I can say, the fundamental principle of homotopy theory that we had yesterday, I want to turn them into homotopies. So in homotopy theory, if I want to get the homotopical analog of this notion of commutative monoid, I replace the set M by a space M, and I want to replace these equalities by homotopies. So I wanted the map that sends x, y to x plus y is homotopic to the map that sends x, y to y plus x. And similarly for the other relations. But now, so it seems like we're done and we know what the notion means, but it's a bit more subtle because there are a lot of hidden relations that these things satisfy. For example, I could have added 4 things together and there are a bunch of relations between those. And the homotopies themselves are also related in interesting ways. For example, sorry. For example, so if I consider the sum x plus y plus 0, then I can use this homotopy to write this as just x plus y. But I can also first use associativity to write it as x plus y plus 0, and then use that adding 0 doesn't do anything. And I get a composite homotopy. And I better make sure that, sort of it seems intuitive that you want those homotopies to be the same. So I want a sort of a homotopy of homotopies in between. But then, these homotopies between homotopies need to satisfy higher coherences. And we get into, a lot of additional structures. So we get infinitely many higher coherences that we want. So it's no longer really feasible to write them out all by hand. But the question is, how are we going to encode them? And the trick is that we are going to write down a suitable infinity category that contains all these higher coherences. So the advantage of the formalism of infinity categories is that our infinity categories themselves already contain a lot of data about all these homotopies. And functors will automatically preserve all this data. So if we construct a suitable indexing category which already contains all the possible relations that we will need, we can just define commutative monoids as functors out of that. That's sort of the idea. So So what we're going to do is we're going to just write down all the possible addition maps, not just the twofold addition maps and the zero. Sort of, we can think of this as adding 2 elements or adding 0 many elements. We're going to encode all the possible multiplication maps go from mn to m. And then we are also going to encode all the possible relations that are going to be satisfied among these. So um, so for any map of finite sets from F1 up to n to 1 up to m, we're going to encode a map F lower sum. Maybe I should explain. So the point is that sometimes we might take sums of sums and we want to take we want to write down relations between sums of sums and something else. So we better make sure that we don't just take one family of sums. We allow the target to be an arbitrary m. And then the map that we're going to encode is the one that sends a tuple xi to the new tuple that takes sums over all the fibers of this map F. So here we're just going to take the sum over all I that are in the pre-image of J. And then we're just going to add up all the xi. And this ranges, the J ranges from 1 up to m. And then finally, we need to make sure what happens if some of these variables are the same. So if you restrict along some morphism, we're going to encode also we're going to encode the compatibilities with the restriction maps F upper star from m to the m to m to the n, which sends a tuple yj to yf of I. Okay, so it all seems a bit complicated, but the upshot is that now we can just write down a category that does all of this. So there's an infinity category called spans of finite sets. The objects are finite sets which are non-empty, so they are in bijection with some set of the form 1 up to n. And the morphisms need to encode both these restriction maps and these addition maps. So we need to encode, we have this n lower bar, and then we have m, and then we have some k. And then we need to encode the contravariant direction, and we need to encode the covariant direction. So these are just maps of finite sets. And then finally, we need to define composition, and composition is given by I'm low on time, so maybe I need to be a bit brief about this. But the idea is that we have some k, we have some map n, we have a map to m, we have some other l, and some o. And then the composition is given by taking the pullback of these two maps over here. And this has some cardinality, so we can uniquely write it in the form 1 up to p for some integer p, and then the outer span that we get is the composite. And now we can finally define what a commutative monad is in C. Namely, it's just a product preserving functor from this span category of finite sets to C. So it sends this n bar to some, let's call this M. It's M and underline. And the fact that it preserves products precisely tells us that this is the n-fold product of the underlying object. And then all these maps in our category, they will encode all these addition maps, all the restriction maps, and all the possible compatibilities between them. But this is sort of the way you would encode higher coherences in infinity category theory. I mean, this is one way. I mean, yeah, there are several different variations of how you could do this, but I wanted to illustrate at least one of those variations. And now we can define symmetric monodal infinity categories. It will just be an example of a commutative monoids. We're just going to define it as commutative monoids in the infinity category of infinity categories. So definition, symmetric monodal infinity category is a commutative monoid in the infinity category of infinity categories. So in particular, it's an infinity category C. It comes equipped with some tensor product map. It also comes equipped with a map from the terminal category into C. In other words, it's some object that we call the unit, and it satisfies associativity, commutativity, and unitality, but up to, we have all the possible coherences that we could imagine. So what are some examples of this? For example, we have the infinity category of spectra. It happens to have a symmetric monodal structure. It is classically called the smash product of spectra, but nowadays a lot of people just call it a tensor product to make the analogy with the tensor product of abelian groups. And another example, if R is commutative, then the derived infinity category of R is also symmetric monodal. And now all the classical notions of algebra, they extend to this setting. So we can define notions of commutative algebras in C things like module categories, relative tensor products, internal homes, and so on. And those precisely encode these things that I discussed before. So if you would do them in dr, then this will correspond to the derived tensor product and to the derived home. Um, yeah, I think I'm already out of time, so I will just stop here.
All right, let's thank the speaker. And are there any questions? Okay. I guess we should start recording.